I try to again to go live just for the testing purposes for tomorrow, just to be sure everything works fine. Okay. Good.
Yes, who's going to host the server today? They said yes. From 5 Bulgarian time, the servers will be hosted from UCF. Okay. Yes, that was we discussed yesterday. For today, it was from our side, from Navy. Now, yes. Could you please check the YouTube link if you can, if you have this possibility?
is to, from the space side, is to get as far off this planet as possible. The game we're playing has some rules. Physics are there. There's not a lot we can do to go get around physics. Teams, team dynamics, how teams work together, our processes, our methods. The science that has to happen or be developed. The story we're going to go tell for what we're doing and how we're doing it. Time is an important part of it. Distance, different cultures, how people work together, goals and the generations that are going to go do the work. All of these drive and either tell us what we can go do or tell us what we can't go do as we try to move to the moon, as we try to move to Mars, as we try to do something very, very large and complex. To start the discussion, I want to share some definitions. We've got 3 of them here that came out. I guess this package, or this concept is going on 18, 19 years old now. I was tasked by a director I had to define the word model for all the things that we were doing, define the word simulation for all the things that we were doing, which is just at Kennedy Space Center. So when I got all the groups together, the definition of a model took an entire page. A definition of simulation was even longer than that. We needed to get it down to something that everyone could agree to. Over a period of time, this is what we came up with. A model represents a thing, something we want to study, and put as much detail into our model as necessary for that study. A simulation represents how that thing or things behave. That's the movement. So, or the behaviors or the changes that occur over time. And again, we just put in as much detail as necessary for that study. And something that we added is we look at the model and we look at the simulation and we make a decision. And we determine what we're going to go do next. So we've looked at the model, we've simulated how they behave, we've made a decision on what we're going to go do, and then it's very, very, very important is to communicate those results to everyone. So that what we've done, what we've accomplished, someone else can go use as the basis for what they did. And we want to communicate our results with enough detail to support the study that we did, and so that someone else can use what we did, so somebody's not continually redoing the work that we've done, redo the work that we've done, and redo the work that we've done. This cycle, model the thing we want to look at, simulate its behavior, decide, and share the results. Repeat it again and again and again and again is how we design and build very, very large, very complex systems, very, very, very complex capabilities. We've got some other definitions. For those that are working with the system engineering community, these come from INCOSE, the International Council on Systems Engineering. That's similar to the handbook that NASA used. And we've got life cycle phases. We've got concept studies. We've got concept and technology development. So we look at our concepts, we look at what technologies we need. In phase B, we're doing our preliminary designs and finishing any new technologies that we need to go look at what we're doing. Integration and test. And in phase E, we operate it, and in phase F, it's close out and do away with the system that we've got. So these are the life cycle phases that we plan. We model and simulate things and make decisions across the entire process so that we can go do the types of things that we need. We've kind of got one other set of things that we've got that are part of the project. And these change as we go across those phases. One of it is the resources. This is typically the money that we've got, or the people that are working on something, or maybe it's the space that we've got to build something. But the resources are to create what we need, and they go away over time because we use them all. So we've got resources that are changing on us, and they go from having a lot at the beginning of the project, and then once we buy things, we've got fewer and fewer built. Towards the end, we pretty much have no resources left, but we've got the product that we wanted. Our flexibility, the ability to change our approach as needed. When we start a project, we've got a lot of flexibility. We can make a decision and decide to go do something, and every time we do that, we lose a little bit of flexibility, but we have to go make those decisions so that we'll get to our end product. Ideally, when we cash in our flexibility and spend our resources, we've got enough knowledge about what we're doing to make sure we made a good decision on what we spend our resources in and what we spend our flexibility on. That brings to the last one, which is the system knowledge. This is the knowledge about what is needed does the customer want? What is required to go solve the problem? What are the pieces going to go look like? And as we learn it, and as we learn data on our system and decide what we're going to go build, this is what we spend our resources and flexibility on. We start with very, very little system knowledge. Ideally, we get smart enough on what the final system is going to be soon enough that we can use that system knowledge to go drive our designs and drive our capabilities. Fortunately, a lot of times that's not the case. This slide you see right here, I call it a classical system lifecycle. I have seen this chart in multiple countries on multiple continents as the problem with system design and system engineering. What we've got here with the vertical line is we're coming out of our phase A, we're coming out of our technology development, and usually we've committed our resources to what we're going to go buy. We spent a big chunk of our money. As we spend our money and we lock things in, our flexibility is going down. So we've got a lot of our flexibility gone. And if we really stop and think about it in the traditional way that a lot of things are managed, we still really don't have a whole lot of system knowledge. We haven't figured out the things that we're going to figure out when we start to prototype and build the concept out. That's just the way it ends up. This was from the original word. First time I saw this was from an aerospace series of aerospace companies at a conference. I've since seen it again, like I said, across the world in many, many different environments. And this is the problem we've got, because by the time we're a big chunk of the way through our design phase, we still don't know what we need to go know. Our flexibility is mostly gone, and we've locked in our resources. We've bought things that we need to go do, or we made design decisions that we can't undo without losing a great deal of cost. The desired world, the types of things that people would like to see, the places that we would want to go be or want to go do, this is what from across the world, again, people want to go see. We'd love to have a lot of system knowledge early enough. We'd love to know what the system is going to look like, behave like, what it needs to be composed of, how it needs to go work, what the interfaces are, and all of those types of things with a great deal of security, while we've still got a great deal of design flexibility. So we know what we're going to go do, and we can just design for what that is. And ideally, we haven't committed a whole lot of resources in this process, so that not only do we know what we need to go do, but we've still got a lot of resources left that we can go spend to go get us where we want to go be. Resources exist to do what we want to go do. This is a very, very information-based process. The previous one was very, very traditional. But the extra information, the system knowledge that we get early is very, very important, and that's what lets us make good decisions early. And if you can go do things that way, life just ends up a lot better.
Mike? Internet connection dropped.
This was a while ago. We approached the problem this way. We had to go deal with solving a very, very large system engineering problem. I want to go share with you a little bit about the Constellation program, NASA's modeling and simulation approach, and MAST was the modeling and simulation teams. At the end of the Constellation program, I managed this project. I had people at multiple centers that were working on this. And we had some partners that we were talking to around the world that were tying into what we were doing. Let me give you some background on the Constellation program. It had three major elements. We had a launch site at Kennedy Space Center. We had the rockets being developed in Alabama at the Marshall Space Flight Center, and we had the crew vehicles where people stayed and where people flew, and those were being built at the Johnson Space Center. The next tier down, where contractors were working, were spread all over the world, all over the United States. And we had partners that were providing systems that would integrate that came from all over the world. We had a system engineering problem. We had to know what were we supposed to build. We had to be able to measure and understand, did we build, did the thing that we built work like we wanted it to? These are classic system engineering needs, classic system engineering problems. That's why the domain of systems engineering exists. Across this, simulation played a huge role for what we were looking for. If we look at our slide beforehand, this is kind of where we were sitting. We were a architect. We were a traditional project. We were looking at low system knowledge. We were where we did not want to be. We didn't have simulation-based content. We had not put the systems in or anything else like that. We had not simulated and integrated them. The booster, the launcher, and the capsules were led by different centers, as I said. And system engineering didn't start in the pre-phase A or the phase A areas. We were into getting ready to go design stuff when we first started doing the system engineering to tie everything together. So where we were sitting across the program is not where we wanted to be. Our system knowledge was very, very low. Our design flexibility was going away, and we were committing our resources. They pulled us all together and said, okay, we've now got this new group. You're going to do the system engineering for all of these types of things. Go. Yeah, you're in charge now. Go. It was not the place that we wanted to go be, but it is the place that we were. So we went forward from there. We had to go figure out a lot of things. We had to figure out what we knew. Step one, what do you know? The systems. What does everybody thinks the piece they're building looks like? Let's get a common version of that and share it with everybody. How does everybody think their part does? That's a behavior. What does their part do when they put it together with something else? So these are our models and these are our simulations. We had to go look at, or these are what we need to build our models, to what we need to go build our simulations. The data that we had was in computer-aided design systems. But they were, in some cases, different ones, and they were spread all over the place, and they were not things that we could integrate because they had not been set up to integrate. We also had documents, thousands and thousands of pages. We had artist concepts and videos of what people thought would behave like. We had presentations and reports that we were able to go gather for what people said in PowerPoint or in a video or in was not, I'm not sure that it was as connected as we would like it to be. And the one thing we didn't have any of was time. The things we just had to rush, we had to hurry. We had a lot of stuff that had to go get done quickly. So given these things, we went through all of what they had and we had to go find the data. We needed numbers. We needed CAD drawings, computer-aided design. We needed dimensions. We needed the mass of things and how it worked that way. The various teams dug into what we were using in Constellation. Our CAD systems were common. ProEngineer for the flight vehicles, at least. So we could go into ProE and go pull that data out, and that was used by 2 of the 3 centers involved. We had supply chain tools, logistics tools. We had discrete event simulation tools. And they were being used for the supply side of things. And that was both the Kennedy Space Center and Marshall. So again, 2 out of the 3 areas were using the same tool, not the same 2 out of 3 as before. We had integrated process analysis tools, very, very highly detailed CAD-based analysis tools. And that was only at Kennedy Space Center. The capabilities of what we were using Domeo for were incredibly powerful, and they let us go look at very, very large integrated systems and pull in the CAD data and go look at it and take measurements and see how things would fit and move and if we could do what we needed to. We had an integrated mission sim capability to pull multiple simulations together and integrate them for multiple parties. And that was at Johnson Space Center, and that was set up by a gentleman by the name of Zach Cruz, who some of you have come to meet over the last year or so. And we had very, very detailed vehicle dynamics using a simulation technology called ScramNet at Marshall Space Flight Center, which couldn't share anything with anybody. It had to run with across computers that were only a few feet apart. We couldn't distribute that out. But the data we had and the numbers lived in all of these tools. We had data management systems, we had common model libraries, we had wikis, and we found out that these tools could go publish information and put them someplace where we could go find it. So that was at least step one, is how do we go find the data and look at it. Data is ones and zeros. When we look for information, it's what we get from a bunch of data. So how things behave, how things work, how things are really going to go play out is the information side of things. We found that in the results of different people's analyses. We found it in recommendations that teams made going forward. We found that in the supporting rationale for decisions, and we found a lot of information in risk assessment. This is what we think could go wrong. This is how we think it could work. This is how we could go recover. So the information on how things were going to go work were spread in different types of documents that we had to go find and look at. And that was going through documentation systems, test results, test reports, presentations. But again, we had systems that we could go get the data back out of. They could publish their information. They could put up where things could be used by others. Then we went looking for the knowledge. We've got the data, we've got information. The knowledge is when this was applied by people who went through the process, what did they learn? Knowledge, we found, comes from experiences. What have you done? What have you learned? What have you seen? What is that based on? How did you go use it? When something happened, who else was involved? What did they learn? What did you know when you started? What did you know when you finished? You know, what you learned going through that process is very, very difficult to share with others. We've got to figure out how to do that to some extent. Because remember, these projects are going on for dozens of years. The people who learned that knowledge are not going to be around when we need that knowledge much, much later in the life cycle. Because it lives in the people, it lives in their experiences. The test team, the analysis team, and the decision makers. These teams are typically our more senior people, which means that they're the ones that are going to go first or retire first. So knowledge is the hardest component to come by. It's very often based on being there when there was the opportunity to go learn it, and not everyone can go be there, because in some cases, the people that need to go use this data, if when we get to the end state, haven't even been born yet. So that's kind of the problem statement. Pulling it all together, we did some things that worked out rather well. We looked at all the physics and dynamics stuff. Flight activities, launch preparations, flight and post-flight, guidance, navigation, and control systems, flight dynamics as needed and where we could, and growing anywhere else as needed and as the data was available. These ended up becoming a lot of physics-based motion, and it was accompanied by the graphical element. So we pulled together the analysis tools, what they look like, how do we see it. We did launches, ascent, docking with the International Space Station initially. Re-entry, descent, landing, recovery, and retrieval, how that life cycle went through it. There were some very high-resolution graphics done for human-in-the-loop testing, what the astronauts used to go train, tied into those systems. And then we had high-resolution graphics for the teams to use to see what the astronauts were seeing, and to be able to go archive those and go share those off to the side so that people would be able to go use them later. In the event of in many cases, much, much later, a decade or two later. We built something called a mission simulation. Modeling and Simulation Labs was MSL1. And it was a full flight simulation from launch from Kennedy Space Center, a couple of laps around the Earth, and dock to the International Space Station. Worked out well. We were able to go see a lot of things, go pull together what we needed, and it allowed us to go chain all the flight dynamics together so that we could see what was done where and how it was done. We used that simulation to go build a virtual mission. All the types of things we did in that lab, plus the build up to it, the preparation and the test, became the virtual mission. This is how do we end to end from factories producing equipment till we get everything launched and up to the International Space Station. What are the parts and processes that we need? And we put that in a sim. Some of it was paper-based, some of it was mathematical, some of it was visual. Our piece was the Ares rocket, the Orion capsule, a launch pad for the ground ops side and their command and control system, and the launch abort system and International Space Station. We had to put them all together, connect them all, make sure all those sims can go talk to each other. And the goal was to find out not what we knew, but what we did not know that we did not know. Unknown unknowns are one of the most difficult things to go find in any project that you work on. The best thing I've found that simulation lets you go see is to discover what those unknown unknowns are so that you can resolve them and know that they're coming ahead of time. What did it look like? This is the Ares 1 launch sim. Kennedy Space Center background, Complex 39. We've got the mobile launcher. which usually you think about it would just sit there, but in actuality, for this particular sim to go work, the mobile launcher was attached to the Earth, and the Earth was spinning, and the International Space Station was spinning above it. So the mobile launcher was treated as an initial stage. It provided guidance, navigation, and control information to the booster so that it knew how to go fly. Our launch abort system used the little pointy thing up on top was the rocket that carries the capsule away. It was done by the Langley Research Center folks. The Orion, which is the capsule, was done by the Johnson Space Center folks. The rocket pieces of the thin booster and the upper stage were provided by the Marshall Space Flight Center folks. I mentioned Ground Ops, Kennedy Space Center provided the booster. And all the communications were done by the folks out at JPL in a model that identified where the communication satellites were and how they could communicate back and forth. I walked in on a meeting where this was being developed that was very, very live discussion. There were some significant concerns that people could not resolve. And the issue that they had is they were trying to get the simulation to work. One of the things they could not figure out who was responsible for in the simulation was the 4 large bolts that hold down the rocket to the launch pad. These are explosive bolts. When the Star booster ignites, they're supposed to be released very, very quickly after that. And then the rocket takes off. But the booster has to be lit before the bolts explode or the rocket will just fall over on the pad. So the work that had been done to gather all the requirements, to gather all the system stuff and everything else, all the work that had been done to harness requirements in the shuttle program, previous things in development, had left that out. The person responsible for the command to blow the bolts was missing. That was an unknown. We didn't know that we had missed that requirement. Don't know how the first launch would have worked. It probably would have been figured out before then, we hope. I believe the wires were there, but there was no system anywhere that was sending the signals. We found out that we didn't know this when we tried to make the simulation work. This is one of the keys for what is there. What had gone wrong is for the Orion, they captured the shuttle requirements for the crew cabin. What nobody captures was a rather large electronics box that sat in the back end of the shuttle orbiter, which was what sent the command that went down actually to the launch pad. So the wires were there. That requirement was captured to tell the bolts to release so that the vehicle could take off. Simulation lets us go find these types of things out ahead of time. It didn't cost us anything. We didn't break anything. We were able to go find the data that we needed and understand things that we didn't know. And for the launches, this then will work. Talked about the knowledge and how you have to be there to go learn it and how you have to go carry things forward. The next job that we had is collect everything that we learned as a part of these processes and save them so that others can go learn what we did. We wanted to be able to go and look at the simulation from the angles. Previous slide you saw was a screenshot, but you can't see what was on the back of the vehicle unless that was going to go be saved and everything was going to go be saved. You can't save that many images, you can't save that many pictures and never get the right viewing angle. So the goal was to save it in something where we could go back and replay this and look at it. You save all of the state information. You've been publishing data as a part of the SIMS to be shared out, and anything that you publish for your state information that the non-federate gathers and sends out, that's now saved. So however many times a second it occurs, your data gets sent out, your data gets logged and saved, and you can go replay it and see what it looks like. This allowed us to go back and afterwards and validate performance. We could integrate those pieces of data that you've saved off for how your system performed with others in the future and see how they work together, even though we were not able to get them both running at the same time, because we know everything that your system did. You know, you can come back and go look at it, how it ties in with something else. You can do quantitative, you don't need more, you've got numbers you can do math on. That's what MPC was designed for. And you can do data synthesis. We didn't have to go save velocity for the rocket or acceleration for the rocket. We know that we've got where the rocket was at 2 points in time, and we can calculate velocity very, very easily. If you want to know what the acceleration is, you can look at where the rocket was at 3 points in time. You can go calculate the acceleration and go save it off if needed. You save the key initial elements and you can go create the additional data as you need it. If you've got an electric motor, you can calculate the work performed by what it lifted and what it did and how much power it used. Don allows us to share the knowledge across the distances so that people can go see what's happening in various areas and go back and forth and go look at it. The MPC data that's generated, in the case of your SIMS by the Don Federate, allows us to share that knowledge along the system life cycle and time. So we've got the ability to go share what things look like and what things were across large distances as well as large pieces of time. And this is what gives us the ability to run these large multi-decadal, multi-generational projects. Or we believe that this is what would give us the ability to go do that. I can share a little bit about some of the things we've done with Don. You can see that a previous version of SCE down on the bottom, but we used it to go plan the habitation modules in the upper left-hand corner for how we're going to go process them and how we're going to go keep them through our buildings. This was a Delmia sim that was done, moved to Don and shared with people in Don. You can see the details for how the crew access the Delmia system that we use from Dassault is incredibly powerful. It's also incredibly expensive, and we only use it in a couple of places or the crew only use it in a couple of places at that night. So it could do the whole launch tower. I could use the crew access arm. It could put people in and everything else. Don has some limitations on the number of polygons you can have and still have it run, so they just cut out the pieces that were important, put them all together, and then did their analysis this way and shared it with their customers. This door here is the door for the Orion capsule. With the detail I needed to see what it looked like, you can see down to the details of where the springs and the latches and the washers are and everything else. You can actually look through the window and see the inside of the white room, where the crew comes in and goes out. This is analysis and what people could see and how they can work together to do what they needed there. So this is one of the ways we're using Don and NASA. Of course, see down here is your SEE from, I think this is 2015, is this screenshot. Lays out the lunar base, the pieces that are there, the different elements that are tied in, and works to get the distributed simulation for us to communicate. The thing that I want to go do as a system engineer, key thing I want to do as a project manager is make sure everybody understands things. A lot of times people aren't seeing the same, where people don't understand the world the same way. Simulation helps us with that. Got a couple of examples that I've come across over the years to help, and I thought I'd share a few with you. This is a building at Kennedy Space Center. To give you a feel for the size, this is a full-size tanker truck. Right here is an Orion spacecraft with the service module underneath it on a hauler that's going to go haul it in and out. What you see here is just the payload bearing, the part that covers the payload for the big version of the Ares rocket. So it's an Ares 5 payload bearing. An Ares 5 payload would go under that and work with. There was a community of people that wanted to work on this and build this up in this building. They did a great deal of study. They got language for the building, and they got the specifications for the building, and they knew that they could work on this particular entity in this building. The thing we were having a very hard time communicating is it's nice that you can go build it in this building, but you'll never get it out this door. And it was a large discussion that went back and forth about, there were ways to go work it. The belief was that this could happen, that people from Kennedy Space Center were having a very difficult time communicating that it didn't. So the team create this image, and we just took one screenshot of the image. We sent the image up to the folks at the Marshall Space Flight Center, and they quit asking. They just asked, it's fine, you can go build it here, but it'll be the equivalent of, and in our country, it's called building a road in the bay. You're not going to get it out once you build it up. So we're able to rather effectively communicate the issues they were looking at there. Other things to go communicating. We talked about the simulation. let us all understand and communicate the fact that we had missed something horrible. Let us discover that we had missed an important requirement in how we were going to go build our system. One of my favorites is this one. Is the Kennedy Space Center Astronaut Beach House. I think it's got its own webpage. It's got a lot of history in that particular building. And we were building, the plan was to go build a lunar lander at Kennedy Space Center. This Constellation program was going back to the moon. And the teams that we had were rather adamant that we could build the lander and do this work here, do this work here. And they had a task sent out for Kennedy Space Center to go follow. It was a touch, from our point of view, unrealistic. One of the things we were doing is we're not real good with the metric system yet, but we weren't at the time. People weren't understanding when something is 10 meters, something is 10, 15 meters tall. The communications back and forth of exactly how big this thing was were not getting understood. So I held a meeting at the beach house, thing right here, and I showed them an image of how big the lander was placed next to the beach house. And they're in the building, there's 30 people in the conference room on the upper floors. They know they're in a 2-story building. There's another 30 of them in there. They know that there's room for all of them. And then the model of the Altair lander is bigger than the building that they're in. So the next piece to go communicate was their plans of putting a 2-story building, or in this case, a 3-story building, on the back of some type of a lifting vehicle and driving it from building to building, up and over bridges, under power lines, and everything else. So we had to. This picture allowed us to very quickly communicate the fact that the building requirement was not, or their transportation requirements were very, very difficult to go meet. And this is how big the lander they were designing actually was compared to the building that they were in. The last one I'll share with you is this poor gentleman, and I believe it was a gentleman. In building one of the vehicle systems, or one of the launch vehicles, we would get a set of drawings in that had been optimized by some software tool somewhere. And it would rotate the rocket this guy is working on, not very far, but looking down from the top in a clockwise direction, about 15 degrees. And we never figured out what it optimized, but it apparently made things work better for the rocket inside. But when it rotated at 15 degrees, it moved this poor guy's feet from on this platform in the background to in the air, about 200 feet up off the ground, or 60-something meters off the ground. The ability for him to go work effectively with his feet 60-something meters off the ground, it just was not going to go work out. So we would feed data back, but I'd modify the requirement, tell them this has to go back this way, explain to people that you can't go do this for these reasons. And the next time the design, the next release of the design concept came out, the door that he has to go work through would be back over this platform. Everybody would be happy until the next release, and it would go move back out. And you'd have to use the same story that you sent before back to go say, no, this is not going to work. This is why. So this went on through 2 or 3 design cycles. And then one of the team leaders commissioned loading the launch pad up, loading the vehicle up, loading the guy up in this particular configuration, pointing out the fact that his feet are no longer on the ground. And the image I've lost is the overhead. Actually, it was a looking up view that it showed that obviously he's 60, 70 meters off the ground. And they just sent these pictures to everybody that was behind moving the rocket back and forth. And at that point in time, the rocket moved back in front of the platform where it was supposed to be, and the next design release came out, it stayed there, and the one after that, it stayed there, and one after that, it stayed there. The simulations let us go communicate what we needed to be able to go tell people, much, much better than apparently words and discussions and meetings were able to. So we're able to go learn things and go see things and go share things, much, much better. So simulation is communication. Simulation is relatively non-threatening. Issues an extension we'll put on a word. I mean, it's kind of, sort of, it's not supposed to be threatening. It's a way to go in and tell your leadership that they're not wrong. You know, it's not having to go tell your boss wrong. You can very gently come in and explain to the leadership team, there's something I don't understand, please help me get the simulation right. And that type of an approach we found works quite often. In this scenario, it's like, geez, sir, I don't know how to have this guy do his work with his feet that far off the ground. Please help me get it right. Please help me, you know, tell me what you understood. Tell me what you were thinking. So it's a way to go communicate in a, I want to say a nice way, but it's a way that lets you focus on the problem as opposed to whether or not someone is wrong. Simulation can also drive out the fact that everyone is wrong. Okay, there's something horribly wrong here. And everybody needs to know something is horribly wrong very, very, very quickly. An example of this would be, I wrote my PowerPoint. Stand by. But it no longer try to page around because it made my PowerPoint very mad. An example of this would be the launch bolts not getting done. The simulation helped us go drive out the fact that every single part of the program had made a mistake. People weren't managing the signal, people weren't generating the signals, and the signals had no place to go. And if we tried to launch the rocket in that configuration, it would not have gone well. My biggest fear, from a project management point of view, from a program, multiple project point of view, from a system engineering point of view, is that we would get three people arguing, say myself and Jefferson and Nicolay. And we've got something that we need to go resolve, but the three of us each have a different vision of what the problem is and a different vision of what we think the solution is. And so we're not really talking about the same things. We've got some flaws in the discussion that we're having. At that point in time, the very, very worst thing that can happen is that Jefferson, Nicolay, and I can agree on something. Because we will have now agreed to three entirely different things. There's the fact that we said we agree, the fact that we shake hands on it, we sign a contract on it, we do whatever. Because we've agreed to three different things, we're doomed to fail in the future. Because only one of us, actually maybe none of us, has the right answer. The simulation, being able to look at the simulation, being able to go study the simulation, using that as the detail that's there, is how we make sure everyone is on the same page, everyone is making the same decision. If we don't have that, if we have a situation where we've agreed to different things, we're going to, you know, our trust model is going to get broken. We're going to start not believing that somebody said, I said this, we agreed to this, how come it looks like this? And you end up with the team can have problems, the team group, the team dynamics can have problems. So that's what I worry about on projects more than anything. Questions? Are there any questions in the room or thoughts?
Any questions?
It's very quiet on the other end.
No, Mike, we're listening very carefully. Any questions, guys? Not at the moment. I see now it's a very interesting topic regarding the concurrent design. This is brand new for Bulgaria, so I recommend to follow very carefully this. Okay, thank you, Mike. We can continue.
Okay. This is another study. This is another, I guess, some learning that we had that things that worked wonderfully well and things that were a bit of a challenge. What you see in the image is from the Constellation days, the types of systems that we were looking at sending to the moon. Different countries were providing different elements of it. The rovers, I think some of the US and Canadian teams were working on. The large spider-like thing carrying the habitation area, I believe the folks at the Jet Propulsion Labs were working on. What we're going to go talk about is the thing on that platform that's got the doors wrapped around it. That's the habitat. That's the place that crews that were on the moon were going to be able to live and be able to go work. So The rotors people had an idea on how those would work. We had examples that were running around. It was this guy and how well you could live in something that was, I think, 5 to 7 meters in diameter. How much work could you go get done in there, and how many people could live with it that really wanted to get a handle on and understand better than what they understood. So the tool, the project was the HDU, the Habitat Demonstration Unit. The goal was to develop, integrate, test, and evaluate its prototypes to better understand how we could go work with them. The project timeline was aggressive. This was proposed well before the June 2009 date that you see sitting there. This was proposed a year or two before. And the goal was to have it, be able to go use it at this field test in September of 2010. And when it's proposed in 2008 or so, 2007 or so, that's a lot of time to be able to go work on something. You make your proposal, your leadership says it's a very, very good idea. Don't start yet, we haven't got the money, but we're going to go find the funding to go do this. And you check with it, a couple of months later. Yes, it's a great idea. We're trying to go do this. And your date is moving forward as you move through time. But this end date does not move, does not change. The end date stays the same. So the amount of time you've got to go complete your project is getting smaller and smaller and smaller every time this occurs. So after about a year, you're not really sure as a project manager that you want this approved anymore, because where you had a couple of years to go build something, now you're down to a little over a year to go build something, and that's a lot harder. Your end date hasn't changed. You still have to go do all the things. All the content is the same, but it's getting squished into a smaller and smaller time frame. Then at one point in time, you hit the point where you say, man, I really hope my project is not going to be approved, because I don't think I can meet that September 2010 date. And then you hit a point in time where you're relatively confident that, okay, there's no way they're going to go approve this, because of course they know that we can't make it. And then you start to sleep a little better at night, and you're starting to realize that this is a chance. And that's when you get the phone call shortly after that says, okay, you're approved, so go. So on this particular one, well past the date that had been supposed to start, with half or more of the life cycle already gone, they got approved in June 2009 to go build something that looked about like these artist concepts and CAD models over here. They had to build the shell. They built it between October of 2009 and April of 2010, but they built it in Virginia, which was a large distance away from where it was going to be used and a large distance from where it had to get integrated. So the pieces had to be shipped. In April, May, June, July, and August of 2010, they actually were able to build and tie together and go work all the parts to assemble the structure, put all of the systems into it, and get it all set up. The 10 months, they ended up with about 10 months of build time and 4 months of system integration time. And then they had about a month that they had to get to the desert so that they could go do the testing. We do the lunar analog testing out in the middle of the desert in Arizona. I think it's just north or south of the Grand Canyon in Arizona, because that one, it's an environment that is very, very similar to the lunar surface. Two, everybody has to bring their systems and bring their systems that far and support them. You can tell the maturity of the system and how things work in that environment and get tied all together. To top it all off, we had the project managed across 3 different time zones with systems that were existing and sitting around from 7 different space centers, probably also some universities and a few other areas. So all this work had to come together in an incredibly short period of time. And it had to all get built and tested and put together. And then the transportation took a number of the months that we had in the life cycle to do it. The job that one of my teams got for all of this was interior design, interior integration. What you can see here are some of the slices of the pie. We broke the system into 8 slices of the pie. And everybody brought their different CAD files in. So we have some stuff done in AutoCAD, we have some stuff done in Pro Engineer, we have some stuff done in SolidWorks, we have some stuff done in CATIA. We integrated all of them together in Delmia, and we could start to see how things looked and see how they went together. And then we could visualize what the final system was supposed to go look like and start to go make decisions. From the time cycle we had, there was only a year from we think this is what it should look like to we have to be done and have to go build it. So there were some traditional requirements process, build it out and play it out. It just was not going to go work for them. There was no time for it. There was no way to integrate it into the timeline. What you can see on this area here, in this orange area, assuming you can see the orange area under the floor, Nikolai. What you see here is an agreement that was reached. The team doing all of the data systems, all of the computer networking, all of the wiring for phones that were in there, radios that were in there, all of the switches and the hubs and all that type of data. They came into they were asked, well, what's the space that you need for networking? And their response was, how many network drops do you need? Which is a valid question. And how many phones do you want? And how much of this do you want? And the response from the integration team was, well, we don't know yet. So the network cannot be designed because they don't have requirements from the phone. The systems can't be designed because they don't know what the requirements are for the network. So what they agreed to was a volume of space under the floor, represented by this yellow-orange colored box. You can see it here. You can see it down here. And they identified a volume that became, I think I can build all the networking stuff you'll ever need in this particular volume if you give me this much space and give me a hatch so that I can get down to it. So the hatch and the volume underneath the floor became the requirements for networking. There was no power, there was nothing other than a volumetric representation that say, reserve the space for me and I can do whatever you come up with. And these types of agreements were made in multiple places around the system. And you'll see just boxes for an element as opposed to a detailed design or capability that's there. And then once the designs matured sufficiently to let the networking team do their job, they went and made sure that what they had would fit within the box they planned out. So those types of agreements and that type of a visual representation and a visual definition of the requirements for system interfaces, there's a new way of looking at things, but there really wasn't any better way to go look at it. And that occurred all over the systems and all over everywhere. It was occurring at such a rate that the documentation for requirements, the design documents, and all those types of things really didn't keep up with the process. And when I was watching the meetings, the screenshot like the one you see right here, or a screenshot like the one that came back here, became the build to documentation. I don't know if that's a term y'all are using, but this became we're going to build it so it looks exactly like this, and it doesn't matter what the drawings say. And it doesn't matter what these other things do, but these became the control documents. These screenshots became the configuration control documents for the entire system. From the point of view of a system engineer, from the point of view of how we were looking at it and working with it, that was a very, very, very scary thing. But all we could do is go watch it because the teams were designing, developing, making decisions, and making good decisions at an incredible rate. It was just quite astounding to go watch how they documented and managed it. When they put all the pieces together, this is what it ended up looking like. And again, you've got rovers from Wind Center, this module built in Virginia and outfitted in Texas. This came from the Jet Propulsion Lab folks. I forget who this ramp came from, but the ramp had to be returned when they were done so that the ramp could not be modified or touched in any way. One of the things they found out in the simulation is this rover can dock to this door, but if they tried to turn the rover around and use the door on the other side to dock, it would hit the ramp. And the ramp wasn't something they could go modify, so that meant the rover could only use the one door to go dock. We had two of these rovers. One of them did not have a door on the right-hand side, so they actually had to redesign the layout inside to get another door that they could use so they could go tie all the pieces together. Their architecture used these rovers as sleeping chambers. So during the day, the rovers were out doing what they needed to do. At night, they were docked, and they provided some privacy and they provided a sleeping chamber. So they had to be able to hook both of them up at the same time. The sim told them that they can't go make the connection the way that they wanted to. This is what the model said it should go look like. This is what we ended up with in the field. Looks very, very similar to it. Played out the road was over the dock here, and the other node was over on the other side to be able to do the types of things that we wanted to go do. We had an ARGIS concept down to some basic CAD models, down to a simulation, down to the system in the field being used for testing. And it was 15 months from approval to the product was in the field testing. Of the first 15 months, a good 3 of them, I believe, were taken up with transportation. This isn't something you can easily drive across the country. It doesn't fit under overpasses, and it doesn't go very fast, no matter how big a truck you put it on. The only real issue that they had is this area, I believe, over here is an air conditioning or climate control system. This system spent the night or every night in a highway rest area or an area off to the side where regular traffic could flow during the day, and they only moved it at night. And one night it was run into by a truck. So they had an accident. Somebody drove into it in a rest area. And the only big issue that we had with the transportation was they had to go down to the local, we call them Home Depots, big hardware store, and go buy an air conditioner they could plug in on the outside and keep it up the air. So the system was 15 months from concept approval to testing in the field. The processes they used for system engineering and system design, from my point of view, were very, very scary. But they were able to go pull all the parts together, get the different pieces in. They built the actual system to go match their CAD screenshots or their simulation screenshots, and built it out that way. At the end, after the project was done, they went back and did the connections to go start to tie things back to what the integrated drawings would look like and everything else. But the gentleman that was doing the work in the CAD system, or in the simulation system, this was his first project he'd ever worked on. This was expected to be an easy one. He just ran with what the teams needed, and they redefined in some cases how engineering could be done and how the capabilities could be brought to bear. So from the current design point of view, we had interesting things going on. We had a parallel development when we got done. The concept phase ran for quite some time, but once a part of a concept was hashed out and was understood, it could then be designed and developed. And while other parts of the concept were still being matured and being pulled together, so it was not only a concurrent design and development and conceptualization, the order that critical decisions were made. Leadership prioritized the decisions such that they made the decisions in the right order. That was a key piece of it as well. For the beginning, I talked to models and things, we simulate things, and we decide and let people know what we decided. Their decision process became very, very important to be able to get this project done in time. And when I talked to them afterwards and interviewed them, the only response I got was just the thought process they put into it was that was the only way they could figure out how to go do it. So we were able to do something incredibly cool in some cases because the team didn't know they couldn't do it. It worked out very, very well and changed how we look at a lot of things. So design process-wise that way, that's pretty cool. Can we use this to go build larger systems? Can we use this to go build new things? It's a question. How will we go formalize this somewhat? We need simulation-based concepts. They don't need to be CAD or they don't need to be SysML. We don't need master equipment to work breakdown structures, any of these things to get our concept right. We need to see what it looks like. We need to see how it behaves. We need enough detail to communicate the integration of communicate the ideas. We need to format it so we can extend it if we want to. We need it quantitative enough to measure, and we need to say so we can share others in the future. So what would this look like? You know, is this a sketch? Probably not, because if we sit down and we sketch something out, it's not really tangible. It's not really integrated. It's very, very difficult to integrate a bunch of sketches together or extend them or measure them. But a sketch is useful because it does communicate your intent. You can distribute a sketch. You can take pictures of it and send it to people. It's rather hard to go to, but it's better than just waving your hands and saying it looks like something. So it is a form of documentation, but it's kind of at a cocktail napkin level of fidelity. We look at art projects, computer-aided art. like Maya or the Autodesk Suite or something like that. There's a rendering of what we want to go do. Does that do what we need? I would say no, because the image is not really tangible. It's not really sufficient to communicate, and it can't really be integrated. Even if it's a 3D modeling system, the way a lot of the models are developed in the art packages don't give you something you can go build off of later. But it does communicate your intent very well. It's better than a sketch, and it can be distributed. It can be recorded. You can make a video out of a lot of these tools and compared to other things. It's still hard to build to, but it is better than waving your hands, and it's better than just a sketch on a cocktail napkin. But a lot of the data, especially the models, can be very difficult to use. Some of you all may have seen that when you try to get a very, very high fidelity model that you want to put into a simulation. The next concept becomes, okay, can I put all this in a video game? I don't really have anything to reason to say we can't do that. It communicates my intent. The game can show me how things move around. A game can be rather easily distributed and shared, but then it can be recorded and it can be compared. The models I put into the game, I can go pull back out and look at and update them. And the game, since it gives me the ability to go move through time and go change things, the behaviors exist, and I can kind of see what I told them to do in the game. So I've got a lot of data that comes out of the game and how the game is working. When I get done with a game-based representation of what I want to do, as a customer, I can hand it to an engineering team and say, hey, can you build me something that looks like this, and build me something that kind of acts like this. It supports representation. The models support representations that allow for system decomposition. But the one thing to do is it uses skills that are not part of the traditional STEM and engineering domain. This is where we start to see the term STEAM. And I think both Nicholas and, Jefferson and Nicolay are starting to talk about STEAM as well. STEM is the science, technology, engineering, and math. He adds the arts to that. And this is something that is much more on the art side than it is on the math side. An artist or a visual arts type capability with a game engine and those types of models can create stuff at an incredible rate. Which is very, very attractive when you're looking at multiple concepts and how to go tie them together. So the benefits of the game, the models are easy to develop and modify, can be generated much faster than we can do CAD. I've seen teams, artists generate a dozen concepts in the time it typically takes to get your CAD system set up and working the way you want it. Models can be shared much easier than with CAD. There's not a lot of property in a 3D model from the game variety. We end up with a lot of data stuck in the CAD system that you can't really pull out. You bring art and design in very early, which lets you go look at things very, very early. And now you get a sufficient representation because through your human systems and people can see what they've designed and they can make changes when it's very, very easy to go make changes. And create your products that can go feed engineering. You use this data to go get your system models, behaviors, concept models, and all of these things are in quantifiable formats. What might be even better than this, using a game for this, would be a game that shows what the concept looks like. So you can share really easy. A simulation driving everything that shows how the concept behaves, because now you can get access to like the real numbers and you can go change them from the sim point of view. Drive them with some math that sits there, and then connect a bunch of them together to understand how the system works. So you've got 3D models, you've got C, C++, Java, some type of simulation tool that's better than the physics in a game engine to see how things work. You can go use HLA to connect them all together and use MPC to go save your simulations, and then design and test systems. And even look at other planets like the Moon, Mars, and space. Or something kind of like this. Does this sound familiar? This is what you guys have built. This is what you guys have done. This is what your teams have pulled together and worked on, is using all of these tools and capabilities to do a great deal of work in the system engineering and system design domain, and create a great deal of knowledge in the system engineering and system design domain. It is my belief that this is the way we should design things in the future. This is the way stuff should work in the future. This is the way we understand complexity. This is the way we need to understand how things work and how things pull together and what dependencies are. And this is how we go communicate critical information to the next generation, the generation after that, and how we go build large complex systems. Questions, thoughts, observations?
Okay. Thank you very much. Thank you very much, Mike. Just what I'll try to do now is to turn off the camera to the guys here, just used to be able to see them. You see?
Hello, everyone.
Hello, Mike. Hello. So,
good evening.
Let me start first with the questions. I'll be the first. This is my honor. Thanks for this.
Just make it an easy one.
It's making easy. Okay. So, really very, very impressive. And I'm really glad to hear for almost an hour your professional background and the history of your life, how you participated in developing yourself and growing in simulation area. I think it could be very good reference and example for all the students here, and not only here, but around the world that are watching us at the moment. What could be after this project? How they can develop their capabilities, and then they can use these capabilities in their professional development. Thank you for showing your experience on that. This is the first thing I wanted to note. And then some specific questions. You hear me?
Yes, sir.
Regarding the development, one of the projects, you mentioned that there were some several models and several projects you showed us. My question here is how many of these 3D models or projects exactly has been implemented in reality? So they have been moved from the virtual life to the real life. I noticed one, but what about the others? It was HDU.
The HDU went through the complete life cycle. For the, I'll do the questions backwards. The HDU went through the complete life cycle, and we got to use it in the field. And that was probably the first real look at how quickly the design process could occur using these types of tools and capabilities. It took a fraction of the time to make major decisions. It was also one of the scarier projects I've worked on, because from the system point of view, really the only documentation we had were those screenshots. And I worked with the manager over the guy doing the simulation work, because he didn't think it could go that fast either. And we were both rather concerned, because there was then one person in the entire project who had used the system, who had set it up, and who had built everything. And if anything happened to him, the project was over, because that's where all the knowledge was. So he tried to build people in that would back up this new guy, and then the new guy was teaching all of the older experienced people exactly how he was doing it, and they all learned. But really the only documentation we had was screenshots for how the system went together, until much later down the path. What you saw on the crew access arm and those types of things, those are the systems that we're building. The designs for a lot of the ground operations activities at Kennedy Space Center, I cannot share. There are things that aren't really supposed to go leave the center. Even if I was still with NASA, I would not be able to go share them. But that image I showed you was an example of how they looked at getting the crew door open and closed. I can share that almost every activity that was important in the UA is done and developed that way at Kennedy Space Center with those particular tools. I've seen integrated design teams sit down and go work through problems. And I've seen instances where the quality people, one of the better examples is the quality people and the safety people looked at what the engineers thought they were supposed to go do, and were able to say, you read that wrong. So when everybody saw the same image, the quality and safety people said, that's one way you could understand what we told you to do, but this is really what we meant. And what we meant is a lot easier to go solve. And I sat in one project where a $5 million project was canceled because the program was planning on doing it based on what they thought the safety people said they had to do, and they had misunderstood. And when the safety people saw what they were trying to do, they were the ones that realized the misunderstanding had occurred. So getting the data in front of everybody helped us. In that case, it solved a $5 million problem. The examples like that are all over the Kennedy Space Center. I can't share the imagery from them. I can't share what's there, and we don't have enough time to go walk through all of them. It would be a good long beer discussion. For the how to carry this forward, the key tenet is make sure everybody understands the same thing. We use simulations, we use the models, we use the visuals to go do that. Get everybody on the same page, get everybody in the same discussion, get everybody worried about the same thing, and then when your decisions are done, you've at least got decisions where everybody's decided on the same problem.
Okay, thanks. And the other question I have here is regarding the HDU project, the full cycle implemented. What was the background, the educational background, and also the professional background of the people that has accomplished this project? I mean, you're talking about designing, but these are engineers, mathematicians, physicians, project managers, something like that. Just to show us how diverse is the team, how many people we need, with what kind of capabilities, just to implement in real life such kind of projects. Because students here, in CE initiative, they can only see the life cycle to the phase of design and making some tests and performance, but in the virtual life. That is what they can see. The step ahead will be to implement them more else in real. So this is, from my point of view, very interesting to share for almost all the cycles, what are the people that have accomplished this project.
Okay, for HDU, and that makes it a good example, the design teams were predominantly NASA engineers. Most of them were very early in their career. Some of the things that were brought in, the system elements that we populated the inside of the HDU with, the tables, the chairs, the glove box that allowed you to work on samples, the medical systems and everything else, those came from different space centers. In some cases, they were student design. Students would come in, or interns would come in for the summer, and they would work out and go build something, and that would be the products were what the students had designed. In some cases, that made challenges for bringing in the CAD associated with it and things like that because none existed. But they had student projects that were in there. The project managers at the senior level were relatively experienced project managers, but they were more of an operations type people as opposed to the classical system engineering type activities. Then that was the people that made the decisions in the only order they could think that it would work. They were treating it as an operational project. What do I have to know first? What do I have to know second? What do I have to know third? So, but they were project managers. They were from operation, I think, and get it done and get it produced that way. They weren't less on design development time. The gentleman that was running the Delmia system, pulling all the sims together, his task was simply collect all this CAD data, put it together, see what it looks like. When his boss, Robert, looked at who's going to do this, he said, this would be a good project for someone to get started with Delmia on. It's relatively basic, it's just an integrated CAD system. So he gave it to the newest guy that he had that did the work. The guy then, as a part of that team, he was the least experienced person on the team. He just did what people asked, show me what it looks like. People kept asking, he kept showing them what it looked like, and the end result was a brand new system engineering method. That was very, very visually based and allowed the leadership to go make the decisions they needed to go make. Somewhere around here are those pictures with a signature on them. Somebody signed them, and that became the approved one because the leadership had signed it. It was really no other way to go track it. So we had, in some cases, student content. We had NASA engineers, or engineers for NASA. We had some project management folks. We had some operational folks in there that were trying to figure out how to go use it. We had some folks from the academic side because some of the systems were part of university partnerships. So we had a relatively diverse team, again, that was spread over pretty much all over the country.
Yeah, very large teams we need for such a project to be accomplished in the best way. And because I'm asking this question because I discussed with the students around here, they have some concerns or hesitations because some of them are now graduating in the military area. Some of them are graduating in the maritime domain, and they have some concerns that are they be able or capable to continue their development even in the simulation domain without having a space background. And my personal feeling is that if you have the skills, if you develop yourselves, this is what I'm mentioning from my point of view, but I'd like to hear your opinion based on the experience you have. That if you want to do something and you just take more skills, learn, it will help you without any space background to grow in this profession, space simulation or even the space industry, right?
Okay. Nothing that was done here, I don't believe, unless you got into some of the orbital flight type work, where we found out nobody had figured out how to release the bolts. That's really the part that would be tied to space. I'm going to put a system engineering hat on, or from a system engineering point of view, is key to understand what you want to do. If you're a project manager, it's key to understand what it's supposed to look like at the end. It's the key to all of this is understanding the work that's to be accomplished and understanding what the end product looks like and working back from there. So the simulation is a very powerful way to identify what that desired end state is, such that everybody can agree to it, and then such that you can go measure against it. That's the key piece. Understanding that from the point of view of, I vowed I would never try to page again. From the point of view of whatever image it decides to put up, it's a matter of representing it so people can understand it and so people can see what they're supposed to go build. I'm looking for an image. In this case, people were able to go build what was in here. This representation, this is currently a space system. It could be a boat, it could be a tank, it could be an outpost somewhere, it could be anything you wanted to go build. The key piece is that there is a representation of it that everybody can see and everybody can understand and everybody can add their value to. And if someone's confused, they can go look at it, and if they're trying to go figure something out, they can go tag it so that, this is something that we have to go see, this is something that we want to go look at. So the skills of understanding how to represent it, and then if you have to go make it move or couple some math to it or couple some physics to it, you can make sure the behaviors are appropriate in what it's doing. Those two are the types an SEE, and they carry over, I think, to any design, development, system architecture, or any type of a project going forward. So that I consider definitely reusable, carry forward. From a project management point of view, make sure you understand what your project is supposed to go deliver. If you're working on a project, and you've got to be subtle in this in some ways, if you're working on something and nobody can tell you what your end system is going to go look like, and there's no way to go represent it, and there's no way to go share it, that might be an indication that someone needs to spend some time identifying what the end system are going to be, identify how it's going to go work, and identify how all that is. I'm not sure I'd stand up and say, well, Mike says you need to go do it this way, because I don't know how well that will go work. But from the point of view of showing what the end desire is and the end state is supposed to go be, these are the most powerful tools I found to go do it. And it can be as simple as doing some basic models. If you want to go connect a few things together and have them run that way, it works that way. If it's a very, very large project, y'all have seen enough software put together to simulate a moon colony in a solar system with the Earth, the moon, Mars, the sun, and a couple other planets moving like they're supposed to. And those are the mechanics and the structure. You understand there's no technical boundaries there. It's just a matter of sitting down to go decide to go represent it.
Okay. So I see that we have 7 minutes to 5 p.m. in Bulgaria, which is 10 New York time. And we have to start testing, but it's very interesting to hear from you what you have done and what you continue doing now. So you have recently retired from NASA, and now you're working as a project manager in simulation in Florida Space Institute. This is something that the students here are not all aware of that. So yes, I didn't make the introduction to your profile, but this is why I'm mentioning this. So you continue your job, your profession, even in the university and academic environment, which is great because that you can share everything you know what you're doing now with all of us here, all your lessons learned, all your bad and good experience, and I'm sure it will help a lot to all the students that will take their path in the career development. Thank you very much again. If you don't have any questions, please have any questions here, guys? Okay. That's at the moment. I think many of the questions were asked by you. If you want to tell something just to finish the presentation.
Okay.
I hope. Yes.
Good. SCE came out. What y'all have worked through and what y'all have built through and the tools you've used to go attach it together. All those types of things are how at NASA we solve very, very large complex problems. What it let us do was see them, understand them, understand the interfaces between them, understand what we knew and what we didn't know. If you can't, here's something that's okay. If you don't have enough data to run the sim, if you can't put it together, if you can't identify enough of what things look like or how they're going to go behave, even just to do a basic sim, either in a game or an animation or something like that, the important piece of information there is we don't know enough about what we're building to go build it. A check can be, can I sim what I think? Can I sim my concept? And the mechanics of going through and just building out even a basic sim or a sketch, a representation, a storyboard even. A storyboard is a simulation. I don't know if that term translates well, but a series of pictures that show from here to here to here to here as you go through time. If you can't build that, there's a strong possibility that not enough is known about the end system to actually go build it. So I know people and have friends in NASA that use the simulations to go check what they had done and define whether or not they had figured everything out. Because if they could hand all of their data to the people that did the sims, and the people that did the sims could build a good simulation of it, they knew they had completed their work. So there's a lot of ways you can use the tools and technologies from SCE to go give you what you're looking for, to go make things better, to go make projects better, to go make systems better. It's all about understanding, and it's all about growing your knowledge so that you understand what you're trying to go do.
So very exciting motivations. I think it will helps a lot the students. And thank you, Mike. Really, thank you very much. I appreciate all the efforts and the whole information you shared with us with this presentation. And I hope that everybody here was able to understand that the simulation is something between science and art. It's not in the middle, it's not in the end of one or the other side, but it's everywhere between science and art. Thank you, and now we can switch to the testing. I hope you will lead this today again.
Yes, I can go do that.
Okay.
I'm looking.
We're stopping the last minute.
No?